hopefully.
It looks like I can... Okay, wait. Can you guys hear me?
Yeah.
I can hear you. This is nice. Finally. Okay, that's good. I don't want to go through my phone. Okay. Let me just get back on to this.
All right.
You can continue.
Okay. Number 3. Does anyone want to answer number 3? Or at least tell us how you thought of how to do it. Did everyone like do it, or are you guys like just not sure how to do it, or are you just don't want to answer?
I got the answer of, could you give me a second? I got 800. I got 800, but I didn't know if you counted 0 as a multiple of 2.
0 is a multiple of 2.
Then the answer is 1000.
Yeah, good job. So do you want to walk us through how exactly you did each of the steps to get your answer?
Yeah. So there's 2 numbers. There's 2 multiples of 4 that are below 10, or like 2 digits that are multiples of 2, which is 4 and 8. There's also 0, but you can't have 0 as the first number of 4-digit number. Also good. So you do 2 times, and then there's 10 digits for the second and third place that are possible. So you do 10 times 10. And then for the last one, there are 5 possible digits. 0, 2, 4, 6, 8. So then you multiply by 5, and then you get your answer.
Yeah, great job. That's exactly how you do it. And one more question. What is the principle that tells us that we have to multiply these together?
The fundamental accounting principle?
Yeah. Yeah,
Yes.
Great job. Okay, nice job. Who would like to, in fact, actually, let's skip the 4th one for right now. 4th one was a little bit hard because it had a lot of casework. It's a little bit hard to demonstrate that on a Jamboard slide. So at the end of the class, I'm gonna tell you guys a shortcut to do that. Because if you did try to use casework, you might have found it a little bit tedious. So I'll show you guys a shortcut for that at the end of the class, because we're in fact going to cover it today. So does anyone want to do number 5 for us? Arjun, is your hand raised for this? Oh.
One's actually...
Oh, Will, do you want to do it?
I did 6 times 8 times 3, and so I got 1 out of 144.
Yeah, except careful one thing. What's the question asking for? Is it asking for the probability or the total number of outfits?
Total number of outfits.
Yeah, so then what would the answer be?
148.
I'm assuming you mean 144, but yeah.
Oh,
yeah. Yeah, you're right. It would just be 144. It would not be 1 over 144 because it's just asking for the total number. So yeah, good job. Okay. All right, this is our homework review. Does anyone have any questions? Okay. All right, let's get started into the actual lesson. All right, so today we're going to be learning, first topic for today is factorials. So I want you guys to take a look at this equation and tell me if, you don't need to solve it, okay? You don't need to solve it, but tell me if there's something new or confusing or just something you notice about it. Wes, do you want to answer?
Sure. This isn't new to me, but there are exclamation points after the 5, 4, and 3, which means that number factorial.
Yeah, great job. Okay. nice, good job that you already know what a factorial is. So yeah, this these exclamation points are called is a factorial. The factorial is an operation. So just like the addition sign is an operation that tells you to multiply two numbers together, the factorial tells you to do something to the number that it comes after. And the factorial is equal to the product of all the positive integers that are less than or equal to that number. So as an example, 5 factorial would be equal to 5 times 4 times 3 times 2 times 1. That is just 120. So 5 factorial is equal to 120. So, and this logic basically extends to any number. 4 factorial would be 4 times 3 times 2 times 1, which is just 24. And 1 factorial would just be 1. And in fact, actually, another thing to keep note, 0 factorial is not actually 0. 0 factorial is equal to 1. I forgot the proof for this again. If you guys want to know why it's 0 factorial is equal to 1, I think Sai can explain because I forgot why.
But yeah, okay. Okay. So there's everybody, if you want, can direct their attention to the Zoom chat feature. So 5 factorial is 120. 4 factorial is 24. But if we notice, 4 factorial is simply 5 factorial divided by 5, right? You guys noticed that, right? Now let's move on to 3 factorial. 3 factorial is 6. Another way we can write 3 factorial is equal to 4 factorial divided by 4, right? So if we go all the way down to 2 factorial, we see that 2 factorial is equal to 3 factorial divided by 3. 1 factorial is equal to 2 factorial divided by 2. So if we were to continue this pattern, 0 factorial is equal to 1 factorial divided by 1, right? So instead of 0 factorial being 0, 0 factorial is 1 factorial divided by 1, or just 1. That's the kind of proof for it.
Yeah, it's kind of a pattern. You have to keep that.
Yeah, it's a pattern. It's a pattern. So don't use your intuition for that. There was there's sometimes where I thought 0 factorial was 0. So yeah, I also thought 0 factorial was 0 until I learned there was actually.
Okay, so in math, especially like AMC and math counts, they like to throw factorial problems because you can do a bunch of different things with them. So we're gonna take a look at some of the things you can do with factorials. So first of all, let's just evaluate them. So evaluate 3 factorial.
6.
Yeah, and it's pretty easy to get it. You just do 3 times 2 times 1. That's just 6. So yeah, this is simple. How about 6 factorial? Yeah, the answer is 720. This is because it's 6 times 5 times 4 times 3 times 2 times 1, which is 720. Or if you memorized what 5 factorial is, 5 factorial is 120. So if you memorize what 5 factorial is, then instead of multiplying 6 times 5 times 4 times 3 times 2 times 1, you could just do 120 times 6. That's because 5 factorial times 6 is just 6 factorial. So yeah, next one. Evaluate, oh wait, I just gave you the answer to that. Oops, sorry, okay. Okay, evaluate 3 factorial plus 4 factorial. Yeah, the answer is 30. Now I'm going to give you a harder one. Let's do 7. In fact, let's not do that. 6 factorial plus 7 factorial. If I don't want you guys to multiply 6 times 5 times 4 times 3 times 2 times 1 plus 7, etc. If I don't want you guys to multiply it out, what would you do to make this easier to solve?
Just memorize, like from the previous problem, 6 factorial 720. We know that, so then you can just calculate from that.
Yeah, that's one strategy. But let's say you didn't know that 6 factorial was 720. What is a strategy, or specifically it's actually a property of numbers that you might have learned in elementary school that you can use to make this easier to calculate? In fact, you kind of basically just used it. You just didn't say it. What is this property called?
I think it starts with a D. Starts with a D, guys. Come on. Distributive.
This is the distributive property. Remember, it's basically where you pull out something from within a number and you put it outside the parentheses and multiply it by the other parts. Well, the distributive property is really useful in situations where you have like large factorials that you don't want to multiply out. You can basically use it to pull out a factorial that you know and then multiply it by a smaller component. So this is another strategy we can use if you don't have them memorized. Evaluate this expression, 4 factorial divided by 3 factorial. Yeah, good job. The answer is 4. This is pretty straightforward because 4 factorial is 24, 3 factorial is 6, 24 divided by 6 is just 4. However, I'm going to also show you the, in this case, it's a little bit overcomplicated, but in larger factors, a better way, instead of just multiplying it out, just notice that 4 factorial is 4 times 3 factorial. So if we pull the 4 out, but leave the 3 factorial there, we can basically cancel out these 3 factorials, and that just leaves us with the answer of 4. Okay, let's go back to the initial one that I showed you guys. Evaluate 5 factorial plus 4 factorial divided by 3 factorial. So for this, I wouldn't exactly recommend you multiplying out. You can if you want, but with larger ones, it might start taking up some time. So, yeah, I'm just gonna wait for you guys to put some answers first.
Is it okay if you're calling someone, Amy?
Yeah, you can call on someone.
I'm gonna call on Manasi to explain. Hello? Would you like to explain? Ended up with 24.
Yeah. So I basically used the same thing as last time, where 5 times 4 times 3 factorial plus 4 times 3 factorial. And then I divided all of it by 3 factorial to get 5 times 4 plus 4 to get 20 plus 4, which is 24.
Wait, hold on. Is this what you did?
Yeah.
Okay, so you basically use the distributive property.
Yeah.
Okay, yeah, that's a good strategy. And why did you use the distributive property?
Because it was easier to cancel out the 3 factorials than to solve through all of it.
Yeah, I would agree.
Could you
So
go the distributive property on how you use it with factorials again, please?
yeah, sure, I can go over it. So in fact, I'll just go over it in the context of this question. So for this question, it would be a little bit slow to multiply it out. Like it would be slower to multiply out 5 times 4 times 3 times 2 times 1. So a way to speed it up would be to use the distributive property. Basically, what you can do is that since notice that like 5 factorial is equal to 5 times 4 times 3 factorial, right? and 4 factorial is equal to 4 times 3 factorial. So if you put these into the equation, you get 5 times 4 times 3 factorial plus 4 times 3 factorial over 3 factorial. So what you can do is you can use the distributive property to pull these 3 factorials outside of the parentheses. So you can get 3 factorial times 5 times 4 plus 4 over 3 factorial. So now what you can basically do, you can just cancel these out. And what you're left with is 5 times 4 plus 4. And that's pretty easy to calculate. That's just 20 plus 4, which is 24. So that's how you use the distributive property to, cancel some stuff out. Make sense?
Yeah.
Okay.
Which is, does that say 5 times 4 times? Oh, no matter, God, no.
Okay. Are there other questions? Okay. All right, we're going to do some other practice problems on a Jamboard. I'm going to put the link in the chat to everyone. Okay, you guys can just write on the Jamboard, do your stuff. Preferably your answers on a sticky note, but if you want to write other stuff on the Jamboard to like do your work, you can definitely do that.
Yeah, it's not just for your work on the sticky notes. But it's a little more tedious with the having to press every operation and stuff in. But
Yeah, so. Okay, just curious, what is an ifrit?
Wait, sorry, did we just solved that problem on the Jamboard, right?
Yeah.
Okay.
I think everybody's using sticky notes. Once we have answers on both questions, we can just go over them.
Okay, I think we're at the
Yeah,
point where we
we
can
have
go.
Okay, wait. It looks like it's pretty messy, but I think we can go over the answers. And make sure that your thing is on the correct side. Like your answers are on the correct side of the Jamboard. So I think we can go over it now. So um, I hope everybody can see my writing. Okay, nice. So we first take 6 factorial common, right? So in the parentheses, we would get 1 plus 7. Okay, and then we divide by 8 factorial. Now, this is simply equal to 6 factorial times 8 divided by 8 factorial. And we can cross this out to get 6 factorial over 7 factorial, which would give us 1 over 7. So that's the distributive way. Using the brute force method wouldn't be too efficient. But oh man, where's the eraser? Here it is. Yeah, that's how I did that. Did anybody have any questions? Can you guys stop drawing everywhere? It's kind of hectic on the Jamboard. Guys, the Jamboard's really hectic, so yeah, it'd be nice if you guys wouldn't draw everywhere. So our second question, we're gonna be taking 3 factorial common. So we're gonna get 3 factorial, then 1 plus 4 plus 5. I mean plus 20. I said 5. Yeah. The reason why it's plus 20 is because 3 factorial times 4 times 5 is 5 factorial. So we have to do 4 times 5, which is 20. That's
You can just do Control Z a couple of times.
Oh yeah, I could. Oh man. Okay, over 6 factorial. So then if we crossed this out and this out, we get 4 times 5 times 6, which is just 120. So you get 25 over 120. And when we simplify, we can just cross out 5, so we get 5 and then 24. So our answer is 5 over 24. So it looks like the majority of you guys got got the right answer. So good job. I think we can move on to the next slide if we're going to move on.
Okay. All right. So now that you guys have grasped the concepts of permutations, I'm basically just going to be using that exclamation mark to denote anytime we're, multiplying factorials. So the next concept is permutations. Permutations, you guys have already been sort of calculating some of it already. Permutations, well, actually, I think it's best to illustrate it using an example. So if you have a question, Michael wants to know how many ways he can arrange the letters in his name. So for example, Michael, that's one arrangement. Mcihealhael, that's another arrangement. Basically, we're arranging the letters in his name in different orders. In each of those orders, each of those arrangements, we would call that's a permutation of his letters, or the letters in his name. And the thing, and I think you guys already know how to kind of calculate the total number of possible arrangements of letters in his name. Using the fundamental counting strategy, we can basically find how many possibilities there are for each. If we consider like there's 7 spaces that we need to fill in his name, and we just need to put the letters in those spaces in some order to represent one arrangement, then for the first blank, we could have 7 different letters because there are 7 letters in Michael's name. However, for the second blank, where the next letter goes, we will only have 6 letters available to us because we already used 1 letter for the first blank. And so for the third blank, we would have 5 possible letters because we already used 1 for the second and the first blank. So eventually this just becomes, so the total number of letters would just be 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is where the factorial notation comes in handy, because I am not going to write that out every time. So that's just 7 factorial, which if you memorize your factorials, you could quickly know it's 5040. So basically that's how you calculate the number of permutations and just a reminder, permutations, in permutations, the order of the objects that we're arranging matters. So in Michael's name, the order of the items that we're arranging are the letters of his name, and the order of those letters matters. I hope that made sense. It's a little bit confusing at first.
I mean, later on, we're gonna get into like duplicate letters, or is that later on this week,
That's
or is it
later, hopefully later today. Hopefully later.
Okay, yeah, making
today.
sure. Okay,
Yeah.
with that, I think we can move on to the next slide. I got this slide.
Okay.
Oh God. Okay. This is a so the thing that we just found out is a permutation. So a permutation is the number of distinct ways you can arrange a group of objects, such as letters, where the object's order doesn't matter. This is something really
Does matter.
important. Wait, oh,
Does matter.
yeah, it does. Sorry, I'm really sorry about that. Okay, so this is like the biggest difference. Actually, I think it's the only difference. It is the only difference between a permutation and a combination. Order matters versus we haven't even gotten to
Well, combinations, you probably saw it in the title
we
slide.
haven't gotten to
Permutations and combinations are related, but there's two differences actually between them,
Yeah.
which we're going to go over at the end.
Yeah, okay, but a huge difference is permutations is where order matters, and combinations is where order doesn't matter. And that might sound confusing now, but we're gonna get like deeper into that later on in the presentation because we have examples that can really clarify that difference. So think about some other situations where we need to count the number of permutations. I have one, you know, the Powerball, like you know how they like draw like the different balls? Like there's a bunch of different permutations for like combinations of like total number of things. And then like a locker combination. Amy thinks it should be called a locker permutation.
They should be.
Because-
Mathematically, they are permutations, but they're
Amy
called
thinks it's
combinations in everyday life.
Yeah.
Do you guys have some other examples of situations where you need to order something? How about ordering a closet? How about a bookshelf of books and you want to order them and place them in a certain order? Yeah, so basically, this is just a lot of permutation is so. All right. Okay, now we are going to go over some more practice problems on the Jamboard. So switch back over to the Jamboard and we are going to take a look at some problems. Yeah, okay. Okay, we are on slide number 4, where it says Alice has 5 cards numbered 1 through 5. How many ways can she arrange the cards in a line such that the number 5 is always in the leftmost position? So you guys try to solve this problem, and once you get your answer, put your answer on the slide.
Okay, looks like we're already getting some answers and one answer. Well, there's some answers in the chat. So
Yeah, there's some answers in the chat too.
let's okay, yeah, so 24. So I'm gonna call someone. Anand, explain how you got 24. Anand?
Oh, yes, sir. I was from mention. So I got 24 because first one has to be 5.
Exactly.
And the other 4 cards could be any number 1 through 4.
Mhm.
So then so the first card could be 4, and then second card has 3 possibilities, and then doing that you get 4 permutation, which is 24.
Nice, that's perfect. That's exactly how you solve the problem. Good job. Oh,
Yeah.
I mean, the factorial looks like a 41. Maybe like
Oops.
put in the dot a little clearer. Okay, okay, that's a scribble dot. Okay, yeah. So that's exactly how you do it. Good job. So if everybody understands that, we can move on to the next slide.
Okay. Oh, it looks like someone put it. Oh, I assume this is for the previous slide. So I'm just gonna move it over there. There. Okay.
You guys need to think about this next problem. So think about this before you answer.
Okay. You need to schedule 5 classes for the day. algebra, history, English, biology, and physics. However, you don't want to have biology, physics, or algebra directly after each other. So how many ways can you schedule your classes? And just to clarify, a class sequence of algebra, physics, history, biology, and English would not be acceptable because algebra and physics are directly after each other. Think about it. This question might seem kind of hard, but there's actually a way to do it. It's actually pretty easy. I feel like you guys are sort of on the right track, but like you, okay,
Sorry.
someone, oh, okay.
Okay, so you don't want to have biology, physics, or algebra directly after each other, right? So how many different orientations of biology, physics, or algebra can we have?
Oh,
What
someone's writing
position
on
must-
slides.
Oh.
Yeah,
Okay.
wait, who's writing? I think you probably
Well,
know.
guys, just think about this really quickly though.
Yeah.
If you don't want to have biology, physics, or algebra after each other, there's only one possible way we can arrange those three classes. Well, there's multiple possible ways, but there's like one possible orientation is
There's
that
only one set of positions they can be
the
in.
set of positions. Well, even that is a little, yeah, I don't know exactly how to say it, but yeah,
Set
there's
of
only like one
positions.
set of positions, like which you can arrange those three classes. So what set of positions can you arrange those three classes in so that biology, physics, or algebra are not directly after one another? Hello? Is there anybody here?
Yeah, they're here. Yeah, Arjun, that's right. You can only put them
Yeah.
in the first, third, and fifth positions. If you put them in any other position, there will be two classes that are directly after one another, and that arrangement won't be valid. So in fact, the only places where you could put algebra, physics, and biology is the first, third, and fifth class.
Mhm.
And that
So
would
I'm gonna
mean that
ask you guys
history.
another question. I'm
Yeah.
gonna suggest one more question. So now that we know that biology, physics, or algebra has to be in the first, third, and fifth slot, how many ways can we arrange those three classes to be in those three slots? It should be pretty straightforward. Exactly, 3 factorial or 6. But now we have two other classes. How many ways can we arrange those two other classes? 2 factorial. So what's our answer? 2 times 3 factorial is 12. It looks like you worked that out, Arjun. That's really good. Yeah, good job, guys. Yeah, the answer is 12. So for you, like for those of you guys who didn't understand, basically we need biology, physics, and algebra to be in the first, third, and fifth slots because there's no other positions they can be in, which satisfies the constraint of the problem. So within their first, third, and fifth position, there are 3 factorial or 6 ways to arrange biology, physics, or algebra. And then we have 2 other classes, and there are 2 factorial ways to arrange those 2 other classes. So we get 3 factorial times 2 factorial, or 6 times 2, which equals 12. Does
Are there-
everybody understand? Because if everybody understands, then we can just.
Okay. Okay, we're gonna move to the next question now. Lily's locker combination, which of course should actually be called a permutation mathematically, consists of a letter followed by a digit followed by another digit, which can be the same as the first digit because it doesn't say that can't be the same. How many possible combinations does her locker have?
It looks like we're getting like some answers. So let's work through this. Actually, I'm gonna give you guys like a minute more. Look at 3 of you guys haven't answered, so oh, not 2 of you guys. I think everybody should answer. Everybody try to answer, please. Because there's 7 people in this classroom and only 5 of you guys have answered, so. Well, it's fine. If you don't answer, it's fine. I guess we can just work through the problem. Okay, now only 1 person has an answer, which is good. That's good. Okay. Let's start. Okay, so how many letters can we get for the first letter? 26, right? Amy, can you write 26?
Sure.
Okay, so how many digits can we get for the first number? 10. How many digits can we get for the second number? Nope. This is where you guys have to be careful. Read the problem carefully. It says followed. Wait, I thought it said different digit.
It just
Never
is
mind.
followed by a
10.
digit.
Oh, my bad. Okay. Never mind. You guys are right. But yes, sometimes it's going to say different digits, so be careful for that. Yeah, followed by another digit. 10. So our total answer is 2,600. Good job.
Yeah. And
Nice.
I think some of you guys thought this would be a problem where you would need to do factorials and arrange things. Well, here's the thing. There's a lot of different types of permutation problems. Some permutation problems basically already give you the objects. For example, the question about arranging the letters in Michael's name. That one already gave you the possible like objects, and you just need to like arrange them. However, other permutation problems, you need to actually choose those objects, such as in this problem, because you're actually choosing the letter, number, and the number. So yeah, in both questions, consider what the question is asking and how you would use the fundamental counting principle to do it. Okay. All right, this question.
I thought it was 3 numbers, not letter and then 2 numbers.
Wait, could you say it again?
I thought it was 3 numbers, number, not letter, number.
Oh, okay. That's all right. Yeah, just make sure to read the question. So yeah, that's okay. Okay, this question is a bit tricky. It's okay. It's okay if you guys don't understand it, and we might have to move on before you do. But hopefully,
this problem kind of makes some students struggle. But like, because I think the biggest thing to struggle on is like kind of understanding the figurative meaning of the box. Like, it's not like legitimately like a box that's separating like.
In fact, let's just remove those for right now because that was part of the accessories. Ignore those rectangles for right now.
First, you guys can try the problem, and we can explain it to you. It's a pretty tricky problem, so
in fact, I'll ask you guys how you got your answer first and how you approached it first.
Yeah, it's definitely a trickier problem.
Would it be 6?
I think you're on the right track, maybe.
Look, why don't you try to explain how you got to this? Well, it's fine if you don't want to. Wait, yeah, we might need to move on before we get to exactly finish this problem.
Yeah. Okay. Since most of you guys answered, I'm gonna ask someone. Does someone want to explain how they approach the problem? I don't expect you guys to get it right because right now we have everyone has a different answer. That's fine.
What I did was I basically arranged them instead of 5 people. I arranged them into 3 people because that's how the seatings would work. There would be Alex by himself, and then there would be Bailey and Derek, and then Edward and Clover, and then I just did the factorial.
Okay.
Wow.
And you know what? Hold on. Let me ask you. Why did you do them as 3 people and not individual people?
because it doesn't matter that they're individual people, because there's three possible like seats, kind of, because one can't sit in between. Say there's 5 seats. Alex can't sit in between Edward and Clover or Derek and Bailey. So it's basically as if there were only 3 people, really.
Yeah, that's a great way to put it. So basically this strategy, we just, for the moment, we're basically pretending that Edward and Clover, we're going to consider them as one unit, and Derek and Bailey as one unit. And because no one else can sit in between them. And Anand, you're on the right track. However, there's another, and what Anand did, he basically is using, so he's arranging these 3 units of people. So Alex, you have Alex, and then you have the Edward and Clover unit, and then you have the Derek, or is Derek? Yeah, Derek and Bailey unit. So that would just be 3 factorial, because 3 times 2 times 1. However, Anand, I think there's still another few steps you have to do, because you
there's just one more thing that you haven't considered. So think about this. What if Eric and Clover could switch seats? That's all I'm gonna say. But think about that, then give us your new answer.
So then it would be 2 possible seats for those 2. So then it would be 3 factorial times 4 or times 2.
Well,
Okay.
yeah, Clover and Edward can.
4 factorial.
Yeah. So Clover and Edward can switch seats, and then Derek and Billy could switch seats, right? So
Right.
so we get 2 times more combinations for Clover and Edward, and then another 2 times more combinations for Derek and Billy. So it's 3 factorial times 2 times 2, or 24. That's our answer.
So 4 factorial, basically.
No, just
Yeah,
4.
basically. Well,
Oh wait, yeah.
not
It would just be 4
You
factorial.
could simplify to 4 factorial, but I mean, there's no point in doing that, I don't think, because it kind of like misrepresents the
Yeah.
problem.
Yeah, we didn't actually get it from 4 factorial. It just happened
we
to end
did
up like
yeah.
that.
Yeah.
You don't want to misrepresent the problem approach, because that could be like.
Yeah, so okay, you guys actually got this pretty well. Are there questions? If you have questions, here's the time to ask. Okay, this next question.
Okay, so now we're going to be introducing the repetition of letters when we're arranging this.
So yeah, how many ways are there to arrange the letters in the word banana?
Well, I mean, is it not 720 because there's letters that repeat?
Yeah, there are letters that repeat. And so that's why it wouldn't be 720. Basically, in fact, let me just explain why it would not be 720. If you look at this right here, the sequence of letters BANANA, this is one arrangement of letters, right? But if you consider every letter to be different, then that means if you switch the ends around, this should be considered a different arrangement. But is it actually? No, because the ends are identical. So this is why there aren't actually 720 arrangements.
Yeah, so there's a way we do this. Let me get onto the Jamboard really quickly. Okay. The way we do this, I'm actually, okay, here. Okay, so here, I was lagging for a bit, so 6 factorial, because there's 6 total ways, divided by the total number of repetitive letters. So there's 2 repetitive ends, so we do 2 factorial, and then there's 3 repetitive a's, so then we're gonna do 3 factorial here. Because that way we divide by the total combinations of repetitions. So what that gives us is 4 times 5 times 6, and then we can just simplify that to 6.
Yeah, and let me just explain. Why are we dividing by the factorial of the number of repeated letters? The reason is because if you notice for the ends, if you consider these 2 ends as different letters, then if you just take them out, there are 2 factorial ways to arrange these n's by themselves, which means that there are 2 factorial ways that this word, like if we just did normal permutations without considering that they're repeating letters, some of the arrangements would be counted twice. So we have to divide by 2 factorial because 2 factorial is the number of ways we can arrange these repetitive letters within the word. And the same logic applies to the a's, which is why we have to divide by 3 factorial, because there are 3 a's, which means there are 3 factorial ways to arrange these a's within the word. And each of these arrangements gives us a repeated permutation. So in fact, let me check ahead. Okay, there's one more of the repeated ones. So let's do one more repeating example. How many ways are there to arrange the letters in the name Jonathan?
Okay, remember, I'm gonna call on someone to explain. Everybody put their answers, but then I'm gonna call on someone at the end. This problem. Okay, so it looks like we got a couple answers. I'm gonna call on someone to explain. Sanvi. Yeah, do you want to explain? Hello? Okay, well that's fine. Mane,
Yeah.
can you explain how you do this? How we do
Uh,
this?
so I think I messed up in my answer, but because Jonathan has 8 letters, we do 8 factorial, and then there's 2 n's. So we divide it by 2 factorial, and then we divide it by 2 factorial again because there's 2 a's.
Right.
That would be 10,080.
Yeah, that's
Nice.
exactly right.
Exactly right. Exactly. That's you didn't mess up. Nice job. Nice job.
Wait,
Okay.
so it'd be 8 factorial divided by 2 factorial divided by 2 factorial?
Yes.
Okay.
Yeah. Divide by these because of the repeated letters. Okay. Questions?
So if there were 3 n's, you divide by 3 factorial?
Yes.
Okay.
And if there's 4 n's, you divide by 4 factorial. So, yeah. Okay. I hope you guys understand permutations because now we're moving on to combinations. Okay, Sai, do you want to explain combinations?
Yeah.
Okay.
Our computer's being a little weird today. I don't know why.
Oh, okay.
It's taking too long to load anything. Maybe because of my Wi-Fi, but consider the question. Michael wants to know how many ways he can arrange these letters in his, wait, my bad. I'm on the wrong slide. That makes sense. Okay, Michael wants to pick a random combination of 3 letters from his name, and each letter can be picked only once. So for example, Mike, M-I-C is one combination. And there are like other combinations like A-E-L, I-C-H, M-I-H, M-E-L, right? But then there are some combinations that would be considered the same thing, like E-A-E-L, L-E-A, E-A-L, and E-L-A. And this is where I actually want to like really differentiate permutations and combinations. So if we looked at this in a permutative, I don't even know if is permutative a word?
That's okay.
If we looked at, I think it should be a word. I think permutative should be a word. It sounds like a word. If we looked at this in a permutational I think that's a word. A permutational perspective. Then AEL, LEA, EAL, and ELA would all be considered different permutations. And the reason why is because they're just different. They have different arrangements of letters, right? And that's because order matters. So AEL and LEA would be considered different because order matters. However, in combinations, AEL, LEA, and EAL and ELA are considered different combinations. I mean, are considered the same combination because they're composed of the same 3 letters, and in combinations, order doesn't matter.
Okay, so yeah, basically, Michael wants to figure out how many of these 3-letter combinations picked from his name there are. And in fact, a way to basically, this is a combination. A combination is the number of distinct, it just means different ways that you can select a group of objects, such as letters, where the order of the objects that are selected does not matter. This is different from a permutation, because in a permutation, you are arranging something where the order does matter, but in combinations, you're usually selecting something where the order does not matter. And basically, anything that involves selecting a group of objects where like the order doesn't matter, that's a combination. So anyone have any ideas for what could be considered a combination?
Yeah. We're gonna get into like that notation a little later.
Yeah, we'll get into that later.
Yeah, so I have a good version of a combination. Okay. I think I have I have an example of a combination. Let me think. I forgot my example. Wait, I actually
did it have something to do with choosing 3 chairmen from a group of people?
No, yes, it was a team. It was a hockey team. Yeah.
Oh,
so
okay.
Choosing different positions in a sports team. That was my example.
Yeah.
Like out of like 10 people, you have to choose 3 for the starting lineup, like a hockey person. I mean, a goal person. I actually don't know the positions of hockey, so I probably shouldn't use hockey as my example. Let's use football. You need to get a quarterback, a wide receiver, and a tight end for your offense. And there's 5 possible people. Different arrangements of cars in a parking lot. Well,
maybe in some situations, maybe. That might actually be a permutation though, because in the arrangements of cars in parking lot might actually matter.
I think it's gonna, because it depends on the size of the car, like where they are in position to the other cars, like whether it's a handicap. There's a lot of factors, so maybe. But if you look at it from like the simplistic perspective, then yeah, it could be considered a combination.
Maybe. Okay, so in fact, I think Arjun already put a hint of what we're just going to show you. Basically, hold on a second. I feel like, hold on. Okay, there we go. All right. So going back to Michael's question, he wants to choose he wants to find how many combinations of 3 letters we can choose from his name, where the order of the letters does not matter. And so what we can do is we can first approach this problem from a permutation perspective. So normally, if we were just choosing 3 letters, we would do, well, first he would have 7 letters to choose from, and then he would have 6 letters and 5 letters. So that would just be 7 times 6 times 5, and that is 210. This is not right. And the reason is because there are repeated, sort of similar to like, remember like repeated letters. Basically, if we have 3 letters, right, then we can just look at this as an example. If he chooses the letters MIC, if for using this our permutation strategy, we would get that MIC, MCI, ICM, IMC, CIM, and CMI are all different. But in reality, we just want the combinations. We just want those 3 letters. We don't care about their order. It would just be an N, I, and C in no particular order. So if you notice, for every 6 permutations we get, there's actually only one combination. And it's no coincidence that 3 factorial equals 6, because these 6 permutations represent the 3 factorial arrangements of any 3 letters. So in fact, what we have to do is we take 210 and we have to divide by 6, or in this case, actually just dividing by 3 factorial. And I know someone asked if the answer is 35. It is 35. This is because, just to recap, we did 7 times 6 times 5, but we have to divide by 3 factorial because we're choosing 3 letters, and to go from permutations to combinations, every 3 factorial arrangements has only one combination. I hope that makes sense. It's a little bit complicated to explain.
Yeah,
but
now I think we're gonna get into like
a formula.
formulas, exactly.
Yeah. So
Now we're gonna be getting into we're a little past. Okay, we're almost
yeah, we
there
should.
anyway.
Okay, once we finish this,
No,
we
no,
can
no,
take a
okay,
break.
we're actually close. Amy, I think we're close enough to our break time. We're only a couple slides away, so maybe we should just continue on.
Yeah, we can just continue on.
We're almost to our break period, guys. We're pretty close. So this is the formula. Yeah, Amy's gonna do a recap.
Yeah, basically, because I know that was sort of a lot. Michael's name has 7 letters in it, and there are 7 times 6 times 5, which equals 210 permutations of 3 letters for Michael's name. However, there will actually be 7 times 6 times 5 divided by 3 factorial, which is 35 combinations of 3 letters for Michael's name. And we divided by 3 factorial because for every combination of 6 letters, there are actually 3 factorial 6 permutations. So we have to divide out those permutations to get to the combinations. So we can call this as 7C3 or 7 choose 3 because we're having 7 objects, which are the letters in Michael's name, and we're selecting 3 of them. And Sa's going to go over the formula.
Okay. So the formula is C n k, or n choose k, and that's equal to n factorial over k factorial times n minus k factorial. So I'm just going to emphasize one thing. N is the total number of objects, and k is the number of objects we are choosing or want to choose from the n total number. So 5C2 is simply, we have 5 things and we want to choose 2, okay? So, and this obviously it's where order matters. I mean, order doesn't matter, right? Because it's combination. The order does not matter. So can you guys calculate 5C2? But just using the formula. And there are shortcuts actually.
Yeah, yeah, we can show you a shortcut.
We can go over the shortcuts after the break, maybe on like the Jamboard. 10. Nice, guys. Okay, 10 is the correct answer.
Yeah, what I would
4C3. Okay, you can just go over the shortcut now, Amy.
Yeah. The way I would calculate this is 5 times 4 over 2 times 1. You might notice that this actually doesn't match the formula because this says n factorial. So technically this should be 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. But as you might have noticed, that's quite a lot of stuff to write. And in fact, this part will always cancel out. So the way I just like to think about it is that for the numerator, you do n times, you kind of do a factorial, but you only do it to the k times. So like, for example, we just do k factorial on the bottom, but for the top, we only do the same number of times as the length of this factorial. Oops, yeah. Okay, so you can do the next one.
Okay, so what is 4 choose 3? 4C3. 4, exactly. Nice. We're getting fast. How about 9 choose 3? Okay, 84. Nice. So it looks like you guys have like really nicely grasped the formula for combinations, and so we can expand these combinatorics to any combination problem. So we're gonna actually try some more combination problems. So like you're gonna see marbles a lot, like like a lot. Like, you're gonna see there's a couple of common objects you're gonna see throughout these math competitions. So those include dice, cards, and marbles is one that you're gonna see a lot in like probability and combinations questions. So we can go over this marble question. So John has 11 different colored marbles in a bag. How many different combinations of 2 marbles can you pull out of the bag? So wait, yeah. So remember, each one is a different color. Okay, so we got an answer. Mani, do you want to explain how you got your answer?
So first I did 11 times 10 divided by 2. But that would be 11 times 5, that is 55.
Exactly. So remember, each marble is a different color. And so if we want 2 different marble colors, we just have to do 11 choose 2, right? And remember, since it's combinations, the order doesn't matter. So let's say we get red and blue. Red, blue, blue, red, they're the exact same thing. So we would use combinations. So in order to approach permutation combination problems, first you have to identify whether the order matters or the order doesn't matter. And depending on that, you just implement the formula. So here we can tell that the order does not matter. So we use combinations and we just do 11 choose 2, which is 55. So it's pretty straightforward.
Okay.
Now we can yeah, Amy, go for it.
Okay. Walter needs to choose his classes for the next school year. He wants to choose 2 math classes, 2 science classes, and 1 history class. The school offers 4 different math classes to choose from, 3 different science classes to choose from, and 5 different history classes to choose from. How many combinations of different classes can Walter pick?
Okay, well, we can try this, right? So remember, they offer 4 different math classes. So how many ways are there to just pick the math class? Remember, yeah, 6, right? How about then we have the science class. How many ways are there to, the science class? 3. And how many ways are there for the history class? 5. So I noticed that some of you guys are adding 6 plus 3 plus 5, but remember the fundamental counting principle. Yes, it's 90. We have to multiply instead of add. So remember, think about this like this. Now that we figured out that there's 6, 3, and 5, it's basically like this. Think about it like an outfit problem. Walter wants to wear, a shirt, sunglasses and jeans. If you think about it like that, then you can just see that the answer is 90. Like we're just picking combinations from like a different classes. Think of each class as a different outfit. We choose and each outfit is a different combination of 2 classes. So yeah, so we don't add here. We don't add here, we multiply here. Fundamental counting principle. Just remember that. We can move on.
Yep.
If everybody understands, we can move on. Yandi, yeah, FCP. Remember FCP, don't add it. Amy, you can do this one.
Okay, so for this question, there are 5 identical oranges and 4 identical apples lined up on a table. How many arrangements of oranges and apples are there? In fact, there's a couple of different approaches to do this problem, but they all lead to the same answer.
Remember how we did this before? It's kind of like letters.
Yeah, if you think about the fruit like letters, it becomes a lot easier.
Wait, Amy, are we gonna get to sticks and stones? No, we're
That's
not.
tomorrow.
Yeah, it's tomorrow. I realized.
Dang.
It's because everything in quantity probability is so related. So
Yeah.
it's it looks like we're gonna transition to like a very similar concept so quickly because everything's super related to one another. Wait, we're also gonna do line pathways tomorrow, or is that day after
Yes.
tomorrow?
That's
Yeah, nice.
for
Nice. Tomorrow's class is gonna be fun. Line
Yeah.
pathways are pretty fun. So yeah. Okay, so let's do this. Think about these like letters. Okay, think about
So
these like letters. So
yeah.
maybe go for it.
Yeah, so if you think of them like letters, how many total letters would there be? Well, there's 5 oranges, 4 apples, so there'd be a total of 9 letters, right? So if now you think of this as some kind of weird word where there's 5 letters the same one, and then 4 letters that are the same, then what you do is that you do 9 factorial, because that's how you arrange the letters if there's no repeated letters. and then you divide by 5 factorial times 4 factorial. And I know, I see a couple of you guys got the answer now. You just do 9 factorial divided by 5 factorial times 4 factorial, and that is 126. And in fact, you guys might even recognize this is in fact just 9 choose 4, which also happens to be equal to 9 choose 5. If you decided to do it that way, where you realize that you could choose the positions of the apples first, and then the oranges would just fall into all the empty spaces. Or if you decided to do it where you choose the positions of the oranges first, and the apples fall into the empty spaces, it gives you the same answer, and it's actually just the same thing. So whether you're choosing the positions of the apples or choosing the positions of the oranges, or treating this like a problem where you're arranging the letters, you'll get the same answer at the end either way. So everyone got that? Okay. All right, break time. You guys get 5 minutes to basically do whatever you want, as long as you return here alive. That's like your only I guess.
Okay.
Yeah, I mean, last time you didn't like come. Sorry, last time you were like you didn't come back until like a while.
Well, I was kind of 2 minutes late.
Yeah. All right then.
I had to use the restroom, so it's not like I'm just gonna come immediately. Yeah, 5 minutes. Just Okay, everybody, we're done with our break time. So yeah. Okay, yeah. We're done with our break time. So
Yeah.
if everybody could direct their attention back to the presentation.
I'm gonna quickly
We're gonna go over a review and then we'll just
Yeah,
we'll see the
Simon.
Kahoot first, Amy.
Hmm?
And then we can go to the Jamboard. We'll do the Kahoot first, then we can do the Jamboard.
Now let's do the Jamboard first. There are some Kahoot questions based off the Jamboard.
Mm,
The Jamboard is the practice question side.
mm, mm.
We don't have to go over everything though. So just for
Yeah.
review, exclamation point is the factorial. It denotes the product of all whole numbers less than or equal to the number that the factorial follows. Distributive property is really useful when working with factorial expressions. Permutation is an ordered arrangement of objects. Use the fundamental counting principle to help you solve permutation problems. And finally, combination is an unordered selection of objects. And basically, we use the combination notation to help us solve combination problems. So back to the Jamboard, everyone. We're not going to do all the problems. I think we're going to skip slide 11. Instead, let's do slide 12. So go to slide 12 on the Jamboard where it says 6 representatives. So yeah, 6 representatives need to be chosen from a school club. 3 of the representatives must be girls and 3 of them must be boys. If the club has 9 girls and 8 boys, how many possible combinations of the representatives could the club choose?
Give you guys like 2 minutes. Yeah, think about this, right? Think about this, guys. Think about this. Remember, combinations. My. Oh my. Okay. Okay, guys. I'm gonna help solve this problem. So look, 6 representatives, right? Okay, now we know that they're representatives. There's no other title. So would this be combinations or permutations? Would the order matter or not matter? In the chat, tell me. Does the order matter or not matter here?
I mean, it really doesn't because it doesn't
Exactly.
matter. Well,
Yeah.
also-
Order doesn't matter because they're representatives. They don't have any other titles. So they're all representatives. We don't care if it's A, B, or C, or B, C, or A. It's the same 3 group. So order does not matter. So now we've identified it's a combination problem. So we know that 3 have to be girls and 3 have to be boys. So how do we do this? So how many ways can you choose the girls? Come on, in chat.
Nine combination 3.
Exactly, 9 choose 3. What's 9 choose 3? 84, right? Exactly. How many ways can you choose the boys?
8 choose 3.
8 choose 3. What's 8 choose 3? Well, 8 choose 3 is 8 times 7 times 6. Okay, so it's 56, right? If I'm not wrong.
Yes,
So what's
it's
the answer?
56.
What's the answer?
You multiply them, I think.
Yep.
So we get, let's see, 84, 56.
4,704.
So I
Sides
got
4,704.
Then have
Okay.
to hand the calculator.
Yeah. No, it's, are you sure?
It's 4,704. I even remember. I remember the answer.
Did you do it on a calculator, Amy?
Yeah.
I'm just going to make sure.
It's 4,000. Sorry, I remember the answer from last week.
Let me just 2 minutes, okay? Before times. Okay, yeah, so guys, the correct answer is to actually be 4,704. I never doubted Amy for a second. I just wanted to make sure, you know?
Yeah, basically
No,
just 9 choose 3 times 8 choose 3. That's it.
Some people actually struggle with this problem. Oh.
Or maybe you didn't give them enough time. I don't know.
No, the next one.
Oh, the next one. Okay.
Wait, Amy, did you come up with the name?
What?
Did you come up with the name? Henry's Hamburger Haven.
This is an AMC problem.
I was about to say it should be House. House is better. We need better names.
Okay, yeah. Yeah, for this one, it's not, don't overthink it. Don't try to
No.
force in some combination notation if you don't need it.
This would be my burger. Maybe 2 patties. I get some onions, tomato. Oh, I love tomato, lettuce, pepper jack cheese for sure. I would get mayo. Is there any ketchup option? I don't think
You
I'll
already
take pickles.
checked.
I like pickles. And I don't really like mustard either, so this would be my option. Do we have like a bread option? There's no bread option. That's pretty bad. All right, guys. So look, who put 92? I want to know. Looks like we're getting friends. I'm gonna ask someone to use Will. Will, do you wanna try to do this? Will.
I'm a bit confused.
Oh, how so?
Like,
To embrace confusion.
I don't know
Okay.
how to put it.
Think about this. Think about this. So I can either have ketchup or I don't have to have ketchup, right? So how many options for ketchup are there? Think about that.
2.
So exactly.
Correct.
So how many options for mustard are there?
2.
2. So then how many options for any of these are there?
2.
Exactly, because I can either have them or not. So how many total options are there?
Well, we don't forget about the patties, Sai.
Oh yeah, no, we're gonna do that at the end.
Okay.
Patties don't matter,
Um,
eh? We don't care about
wait.
patties. Not yet.
Is it? So are we doing 2 to the 7th? Or 2 to
Uh,
the 8th?
Yeah.
Yes, exactly. It's 2 to the 8th because 2 times 2
Okay,
times
so
2
that's
is
2.
the
So that's
total amount of combinations.
256.
2
Yeah,
times
so far.
8, right? Yeah. So it's 256. But then think about this. It says we can have up to 3 patties. So how many more combinations is that? 3 patties.
3.
3.
Yes.
So our answer is 768. Great job. That's really good. That's a great job. Nice job. Okay. We're done with that problem.
Yeah. See how this problem's a little bit
let's see.
unconventional. It's not, it is still technically a combination problem. It's just instead of like actually making you like find every single one, you could just look at each component individually.
Yep.
Okay,
This
I
might
have
be
this
our
one.
last problem. I
Yeah,
don't know
this
if we-
one. We
but
might,
let's just do.
yeah.
Let's make this our last problem.
Maybe.
I
Okay.
think because we'll see. Okay,
Okay.
this one is a very difficult problem if you don't know how to do this.
But
I
just
mean,
think about it though.
like,
Think about,
just
use some logic, I guess.
okay.
Anand, I'm glad that you're thinking. But unfortunately, that's not the right answer.
Yeah, think about
Yeah,
this,
that would
right?
be a very, very big number.
Right. I'm gonna give you guys a very
In
quick
fact,
thing.
if you guys
So-
want to, what you can do is draw just one line and see how many intersections there are, and then 2 lines and see how many intersections, and then 3, and then 4. I don't know if you can draw more than 4, but like see if you can find some kind of pattern if you can't figure it out just by using logic. It's more than 10.
Okay, let me explain this to you really quickly, okay?
So
So we have 3 lines, right? 3 lines, right? So the most way that these lines could intersect is 1 intersection per 2 lines, right? So 1,
Yeah.
2, 3. So this is how actually Amy's kind of the one who really like explained this, right? Because I knew the formula for this like beforehand. Like I knew the formula for like maximum amount of intersections for n amount of lines, but like I didn't like completely understand it. But then like I think Amy explained it really well. So you want
Yeah,
to
I can explain it. So again, we are trying to maximize the possible number of intersections there are. So think about it like this. The least number of intersections there are is if every line is parallel and no line intersects any other line, right? So the maximum number of intersections would only occur if every line intersects every single other line. Just do know that the maximum number of intersections two lines can have is one intersection. So to maximize the number of intersections, we have to somehow make every line intersect all the other lines. And we don't actually need to draw it out. We don't need to even try to think about how to like visually represent it. We just need to, if we assume that every line is intersecting every other line, then that means that we should be able to choose two lines and they should be intersecting. And in fact, it shouldn't matter which two lines we choose. As long as we just choose two different lines, they should be intersecting. So in that case, we can represent the total number of intersections as 10 lines, choose two lines. Because what this means, 10 lines, choose two lines, it means that it's the total number of ways you can have 10 items and choose two items, right? And that's exactly what we're looking for the lines. We have 10 lines and we need to choose two lines, because whatever two lines there are, there should be an intersection. And if we assume there is, then the total number of intersections would be just 10 choose two. And that would be 10 times 9. 10 times 9 divided by 2 times 1. Oops, that's a 1. That equals 40.
Amy's explanation for this problem was I think was really well stated. Because the thing is, right, think about it like this. There's 10 lines, right? And when we choose just two of those random lines, they have to intersect, right? So first, back to the basics. Two straight lines cannot intersect in more than one point. Everybody knows this, right? Because we can't have like, if we have this and then this, right? Those aren't straight lines. So two straight lines can only intersect at most once. So in order to have the maximum number of intersections, we need every single line, we need all possible pairs of two lines to intersect with each other, right? So if we chose any two random lines, they would have to intersect with each other to produce the maximum number of intersections. Therefore, we do 10 choose two. So we choose those two random lines, and we know that there's going to be one intersection. So 10 choose 2 gives us the total number of combinations of two lines, and thus gives us the total number of intersections. So
And in
10
fact,
choose 2. Yeah.
this works
Go
with
on.
any number of lines. So if you have 20 lines, you would just do 20 choose 2. If you have 100 lines, you would do 100 choose 2. So pretty handy.
Amy, how many questions does the Kahoot have?
Let's check. Oops. I kind of want to fit in one more Jamboard question, but let me check.
No, we can. That's what I'm saying.
I think we can fit in one more Jamboard question. In fact, let's do the Okay, so I choose a question. I kind of want to, okay, let's do a shape question. Slide 16 on the Jamboard, where it says how many diagonals will a regular convex 20-sided shape have? Slide 16. Oh wait, sorry, are we doing slide 15 or 16?
I think we should just skip ahead to 16 maybe.
All right, let's do slide 16, where it says how many diagonals will a regular convex 20-sided shape have?
Yeah, okay. There's one thing you have to consider. So I think a lot of you guys can actually get this right. But there's one thing. This is one thing that I forgot to consider.
Oh yeah, I remember.
Yeah, I forgot to. I felt so silly. It was the last question. I was about to get a perfect score.
Oh
looks like
wow.
we're already.
Okay.
That was quick. That was so
Yeah,
quick.
that was quick.
That was insanely quick. Well, how did you get your answer? Whoever wrote it. Who wrote the answer? And you can check.
Yeah.
Yeah, money. Did you get 170?
Yeah.
Okay.
Explain.
Well, okay, so I just did it 20 times. I did it 20 times 17 divided by 2. That is 10 times 17.
Yeah, 20 choose 2, right? So pretend.
Oh wait. Oh,
Yeah,
money.
like-
You already know the formula. The
Yeah.
n times n minus 3. Oh, okay. Oh, we were
That
meaning
makes
to do it with the combination way, but that works too.
Okay, so here's the way that we should do it, right? So think about it. There's 20 shapes, right? I mean, actually, your formula is perfectly a good way too,
Perfectly
but it's
fine.
better to understand, in my opinion, than rather memorize formulas. But if we have 20 shapes, right? If we choose any two of the vertices, we can draw a diagonal. There is one stumping that though, which I'll explain later. So we have 20 vertices. So I'm going to use this hexagon. So if we just choose any two vertices, we can draw a diagonal. So in that sense, we do 20 choose 2 and get 190. So we think we have 190 diagonals, but there's one thing. For example, this hexagon, if I chose these two vertices, this is not a diagonal. It's just a side. So we have to subtract 20, right? Because this has 20 sides, and we have to subtract all the cases where when we pick those two vertices, there will be a side. So we just have to subtract 20 and we get 170. You guys understand? I'm gonna make you guys do this with the hexagon. So hexagon, same hexagon, do the exact same problem that I just did with the hexagon. How many diagonals can you fit into a hexagon? This will prove your understanding. Not minute.
Yeah, why is it 9?
Okay, think about this, right? I'll explain why it's 9. So 6 choose 2, because we can choose any two vertices, we get 15. 15 minus 6, because there's 6 sides, we get 9. Okay, Mane, I know that you know the formula, so well, let's give like maybe other people like just a bit of time to like try to solve the problem. But it's great that you know the formula. It's really nice. That's really nice. So let's try 11 side. So how about a regular 11-sided shape? Try this one, you guys. Yeah, Mane, it'd be helpful if you like didn't answer just yet, because I know that you know the formula. So guys, try to answer 11. Wes, explain how you got 44. Wes,
So I did 11 choose 2
right?
and I got 55,
Mm-hmm.
and then I subtracted 11 for the number of sides.
Perfect. That's exactly how you do it. So remember, we choose two vertices to draw a diagonal from, right? Two of vertices, right? Then we have to subtract the total number of sides to get rid of all the cases where those two vertices are create a side of the shape. So good job. I hope everybody understands that, and I think we can move on to the.
Yay. I forgot how many questions there are. So
I hope not side, jump into the Kahoot. It ruins everybody's fun, It's okay, guys. Not Sai will not be joining the Kahoot today. I won't join the Kahoot. Not Sai won't join the Kahoot. Yeah, that's the formula. I believe that's the formula.
yes, it is.
Okay. It's very unfortunate that not Sai will not be joining the Kahoot today.
Well, then that means it's psi, right? Double
Yeah.
negatives.
But it's not Sai, so. Five people. We have 7 total people in the classroom. I can start the game. Oh, 6 people. Nice. Okay, just start. Start the Kahoot.
All right. Oh God. My volume is
No,
really
I'm
loud.
gonna challenge myself to not use a paper for the entire thing. That way it might be a little more fair.
What is this math
This is a
symbol
hard.
called?
Amy, why'd you make this Kahoot so hard? What the heck?
I don't know.
Okay, skip. Oh, there's never mind.
No, it'll skip automatically.
Wait, no way, dude. I'm in 4th place. What the heck?
Oh wow. It's so close.
Okay.
I don't know why I put 30 seconds for this, but okay, that's all right. Yay! Oh my gosh, you guys have gotten the first two questions all right.
Nice. That's good.
Really amazing. 6 factorial plus 4 factorial divided by 3 factorial. I think I put too much time on this, but okay, it's fine.
I'm gonna get this wrong because I don't have the paper.
Yeah.
Well, actually, how can I not solve this?
And I'm very confused. I feel like what I got isn't on the thing.
Yeah, what I got isn't on the thing either.
Let me
I-
solve it quickly by myself. Oh, wait okay, let me see. 6 times 5 plus 1 over 3 factorial. No, it's on there.
My answer was on the screen.
Okay, let me just check that real quick on calculator.
Yeah, what? Okay. This
Yeah.
is gonna be. Oh yeah, never mind. It is on the thing.
Okay. Yeah, the answer is 124. I'm just gonna
Yeah, wait, wait.
quickly, actually, I'm just gonna go over quickly. 4 factorial times 6 times 5 plus
Ah,
1
Okay,
over
understood.
over
understood.
3 factorial.
Oh, I did
So-
6 times 5. Ah, I know what I did wrong.
I'm not doing it on paper, so I'm choking a little, but it's fine.
I know what I did wrong now.
Bad mental math skills.
Oh wow, okay. Yeah. All right, ordered arrangement of objects.
I was this close to
Everybody's
missing.
gonna get this right. Amy, everybody's gonna get this right. Trust me.
Oh no, someone chose a combination. Oh no, ordered arrangement is a permutation.
Oh, that's unlucky. Okay,
Selection, unordered selection.
this one's just gonna be whoever gets this the fastest, right?
Stupid internet.
Everybody should get this
It's on a
wrong.
browser and I do the
Someone
night.
chose a
What?
permutation.
Guys,
Oh man, oh man, okay.
you guys are making Amy so sad. Like Amy's sad, right?
Okay, that time it wasn't me.
You guys are making Amy sad. You guys should be like so. You guys should be so sad to make Amy sad. You know. Oh, I got this wrong. There is no way I get this wrong. I'm so stupid. I got this wrong. I put 15 to 20.
Oh, Sai. You're Sai, you're the only one who got it wrong.
You just gave the final answer to the final person the
Oops,
answer.
Sai left the leaderboard.
Okay, I'm leaving the good, but I can't do this anymore. Oh my god, I don't know how I got that wrong.
Yay.
What? I don't see the question. Oh.
Sorry, I accidentally made it live by moving the Zoom cameras.
I thought it was gonna be a probability question for a second.
Nope, it's just how many ways can you flip two
I'm
heads?
confused with this question.
Guys, the answer is square. The reason
I don't
why?
think we-
Well, it's not.
Yeah, we didn't
thought-
specifically go over this, so I'm gonna go over this right now. Basically, how many ways can you flip two heads? Well, think about it like this. You have 1, 2, 3, 4, 5, 6 flips of a coin, and you need to choose two positions to be the heads, and all the other positions are the tails, right? So you would have 6 choose 2 ways to flip two heads, and that would be over the total number of ways, which is 2 to the 6th power. So that, or wait, I did the probability, sorry. It's just 6 choose 2, 15. Because you have 6 positions, you need to choose 2 positions to be the heads. Oh, wow. Oh my gosh. That shifted the leaderboard a bunch. Okay, Leo has 4 classes, math, science, English, social studies. How many ways can you schedule 4 classes?
Easy.
Misclick,
Yeah,
Oh
no!
no.
misclick is our worst enemy, guys. We have
Up
to.
there was the last second, there was a misclick and tried dragging into the other thing, but it didn't work.
Oh
We have
man.
to work together to avoid misclicks, guys. We have to avoid
Oh
misclicks.
yeah.
You know what?
This is
Fine.
just
Yeah.
for factorial.
This
That
one's pretty
lost me.
good.
That made me go down by 900 points.
Uh-oh.
Okay. This is the hardest one. At least one person's gonna get the wrong answer. At least one person. At least minimum. Somebody's gonna put
What if
zero.
no one gets it wrong?
Somebody's actually gonna put zero.
What if no one gets it wrong though?
Wait, isn't that the right answer?
If no one gets it wrong, Amy's gonna be
One
happy.
person. Oh
I
no.
told you that.
Okay,
knew
yeah,
I
zero
did.
factorial again. Zero factorial is just one. Oh, okay. Good thing is no one chose zero. That's good.
Yeah, but undefined is like
Okay. How many 4-digit numbers only have digits that are multiples of 3? Remember, 0 is a multiple
whoa,
of
Amy,
3.
don't say anything. I'm trying to win this Kahoot. I'm trying to win the Kahoot. If I lose, it's because of Amy, basically. No paper. I'm not using paper, you guys. To make it fair, I'm not using paper.
Neither am I. This isn't making it fair at all.
Well, you should use paper.
Okay.
I guess
Almost
there's
everyone
no
got
way
it
to-
right.
Nice. That's actually so good. I'm surprised. Happily surprised. It's good that you guys got. Let's go, dude.
Oh no.
Technically, I guess so.
6, choose 2.
Where's the answer? Oh, never mind. Never mind. I'm stupid. The answer's right there.
Yeah, this one's a
I
little
think
bit
some people are gonna
tricky.
get this
It's
wrong.
ki-
I think some
That
people are
makes
gonna get this
sense.
wrong.
The answer's not on there.
It is.
It is on-
It's just in a different form.
It's on there.
Yeah, I kind of expected some of you guys to miss it. Here's an interesting thing. 6 choose 2, 6 times 5 over 2 times 1. 6 choose 4, 6 times 5 times 4 times 3 over 4 times 3 times 2 times 1, which in fact is actually the same thing as 6 choose 5. And notice that 2 plus 4 equals 6, and that is not a coincidence. In fact, 5 choose 3 and 5 choose 2 are equal. 4 choose 3 and 4 choose 1 are equal. I have no idea what 100 choose 90. Okay, I do know what 100 choose 99 is, but 100 choose 72 is the same thing as 100 choose 28. The reason, as long as the last two numbers add up to this first number, then they're going to be the same.
Yeah. So yeah, guys. Yeah.
So that's why
60
whenever you do 6 choose 4, you might as well just do 6 choose 2 because it's easier to calculate and it'll give you the same answer.
Somehow caught up by 1,000 points.
I forgot. I thought I lost something over there. What the heck?
Okay, how many ways are there to arrange the letters in the word Kahoot? And the reason why I used the word Kahoot is because I couldn't come up with a more creative word.
Yeah. Be more creative, Amy.
Yeah.
I'm joking. Amy has a very creative questions, guys. Like, she comes with very, very intricate questions. Amy should be a question. Amy should be a test maker for the AMC.
Yay. Okay. Almost everyone got it. That's great.
Oh, I just realized what I did wrong now.
Yeah.
Oh yeah.
Secret code made up of an even digit, a prime digit, and then a letter. How many secret codes are possible?
Okay, I got the answer. Wait, am I first? Okay, whoever wins this, like I said before, whoever wins this gets teacher status for next class. Yeah, if you have to get first though, you have to be me too. You want teacher status, guys?
Okay. Yeah,
Yes.
this one basically there are 5 possible even digits. You could have 0, 2, 4, 6, and 8. That's 5. Then how many prime digits are there? Well, there's 2, 3, 5, and 7. Those are the only prime digits. 1 is not a prime digit. So there are 4 prime
Yeah.
digits. Finally, there's 26 letters. Multiplying it out, that is 520.
Okay, we move on. We might be a little short on time, so I think we have to be a little more.
Oh yeah, I
fast.
gotta go speedy now.
Speedy McQueen.
Okay, Laura wants to
Oh,
swim
I'm
one
first.
day on the weekend and go hiking 2 days on the weekdays. How many ways can she do this?
No paper.
Oh wait,
No
I just
paper
realized this
necessary.
isn't fair. Sai's already seen these questions before.
No, but I don't memorize them. I don't even know the
Yeah.
answers to half of them. I haven't memorized a single. I'm doing this from scratch, so. Yeah, I actually don't remember any of these. I'm just doing it from. I'm just doing
It
it
was an absolute
from
guess, and that's the
scratch.
only reason why I chose 10.
That's okay.
Okay, so
I'll explain
just
it.
move on. Okay,
She
the
wants-
reason why it's 20 really quickly is because 2 days on the weekday, so it's 5 choose 2 or 10, and then 1 day on the weekend. There's 2 ways we can choose a day on the weekend, so it's 10 times 2 or 20. We have to move on.
Yeah, we gotta hurry.
We gotta hurry.
You'll probably make it because you got 8 minutes and 4 questions.
Oh, well, maybe 5 questions, but yeah, maybe, hopefully.
Okay, I'm gonna give you guys the answer to this one. Okay, it's yellow. Yellow, trust me. I would never lie to you.
It's not.
Next.
Wait, is it yellow?
It is
Hold
yellow.
on.
Yeah, it is.
The reason why
Yeah,
it's
yeah.
yellow,
Okay.
remember what you showed you. 7 choose 2. Wait, I gave you guys the answer.
Did you get it wrong? Okay,
No.
never mind. I don't think they trusted you
Why not?
because you're trying to win this.
No, I'm not. I'm trying to make you guys learn something and win this at the same time.
Okay, yeah, I don't think I gave you guys enough time for this.
Oh my god, I have to guess because I don't have I need paper for this. Well, actually I don't. 6.
You just need time.
No one got it right. Okay. This
You
was the
think-
most creative question I came up with. I didn't give you guys enough time. Yeah.
30.
This one's just a matter of time. Pull out the 5 factorial, cancel it out, and then just do the rest.
Yeah.
Okay. How many different triangles can you make by connecting 3 of the vertices on a cube?
I don't remember these. Okay, guys, to make it fair, I'm gonna get the last 2 questions wrong. Not the last question, just the last question. I'm gonna get the last question wrong. I promise. I promise this time.
8, choose 3.
Guess
8
what
vertices on a
question.
cube, choose 3. It's just 8, choose 3, 56.
What's the gap?
Just 1 question gap. So
Okay,
So
I'm
you
getting the
get
last
that
question
wrong, and Mona gets it right. You lose.
Amy, are you sure you give us enough time for this?
I don't know. I think I did.
Yeah, you caught. Oh yeah, I did it mentally, which is good. So yeah, it's a pretty easy question, but I had no paper, but yeah, easy. I did it before all of you guys.
I just had to guess because my answer that I got wasn't on there.
Okay, so the reason why it's yellow is wait, never mind.
What?
Okay, I already gave away the answer. So the reason why it's yellow is because 2, 3, and 5. So it's 6 choose 2 plus 6 choose 3 plus 6 choose 5. Just do that really fast and okay, I'm getting the last question wrong.
Oh,
Yeah,
Oh, okay, no,
yeah,
you don't.
Oh.
wait, there's a. No, you'll get it. You'll win. Oh,
That's so lucky. I'm just gonna get this right because there's no point in like not getting it right because I know I'm gonna
you
win
don't know
anyway.
that. It's
Yeah.
possible.
No.
maybe
No,
it's
it's not.
possible.
Even if-
It's possible,
even if you
maybe
get-
for.
If they
I don't know.
answered
Yeah,
it
that
like
probably isn't actually.
immediately and also as the first one, and they were on an answer streak, then it's possible.
Okay, yeah. Almost all you guys got it right. Yeah. 9 choose 2 minus 9. Or if you know the formula, 9 times 6 over 2. Woohoo.
I thought
Okay,
that was
Good
how
job,
many-
Arjun.
9 things.
Okay, good job, Manny. Oh yeah, we're not surprised. Okay,
Oh, wonderful.
Manasvi, you're third. Technically, you're third because
He's
Sai
You know, you only missed by one. Okay, so Mane got first, Arjun got second, and what else we got third?
I think I would have gone fifth.
You know what? I'm gonna do it. I'm gonna do it without looking next time. I'm just gonna Amy just read out the question out loud. I'm just gonna use my mental math.
All right. Okay. So good job, everyone, for the Kahoot. Yay. Okay. Yeah, we're pretty close to done. We have like a couple of minutes left. Side, do you want to end early today?
Yeah, but let's end a little early. First, let's go over the homework.
Oh yeah. Okay. Well, homework's there's really nothing to go over. It's going to be on the Google Classroom sometime. If you want to get started early, here it is. If I can find the chat. And yay, question slide. Questions for today and you can ask anything, not just about this lesson.